Okay.
And then
Divide by the smallest. Divide by the smallest. Which one's the smallest number?
These are the same.
Divide by the smallest number.
So divide everybody.
Because that's going to give you what? Okay. Because remember, you got to have whole numbers.
Oh, yeah, that's right.
Oh, don't forget to do this one.
I know. I was just doing that practice.
Just alternate election. Although I don't want to put just something random because I may end up doing that. Because I don't have any Yeah, that's why I was telling me not to put the mythology class. I think it would be good, but if I said this mythology is hard.
Alright, so now what do we do, Cody? Now what did we do for the bell work here? We have 1, 1.5, and 1. So what are we going to do?
Oh, I know.
Oh, multiply it by 2
There we
to
go.
get it all to a whole number.
Great. You got this. Alright, excellent. Then you just do your formula C.
C, H, 3.
What's the empirical formula for benzene and acetylene? Jake?
C8H8.
No, you're close. It's CH. So this will all reduce down, right, to CH. Does everybody see that? Because it's basically a 1-to-1. Does everybody see this 1-to-1? This is 1-to-1. So the empirical is CH. Now, if you were to do the percents, like I'm getting ready to show you, it's going to be a hard time identifying what you have here. So let's take a look at that. Percent compositions. This is out of 100, right? And we're converting it to grams.
That wouldn't equal it.
Yeah, this adds up to 100. Because 5 is 45, and there's almost a 5 there, so we'll equal 100 there. Alright, so we could do the same thing from the actual formula like we did yesterday when we were looking at table salt and how much sodium you can consume per day. It's around 6.25 grams of table salt. Because it's only 40%. So if you take 0.4 times 6.5, you get the 2.5 grams you can consume of sodium. So if we have our acetylene, right, and we do our amount of carbon, which is 24 grams, we have 2 grams of hydrogen, you add that up, you get 26. Does everybody see here we got 26 grams of 1 mole of this? So we have 26 grams here. We take our carbon, put it on top. This is going to tell us how much carbon percent is in the acetylene. So we have 92%.
So 92% of
carbon.
the first one is inside acetylene.
Right. There's 92% carbon in acetylene. Does everybody see that? Yeah. Now if we look at benzene, we have our formula here. We go to the periodic table. We get the carbon. 6 times 12 is 72. 6 times 1 is 6. You add that up, you get 78. Does everybody see that?
Yeah.
So we then put our 72 on top, divided by the 78, and we get 0.92. It's the same thing. So they're both 92%. So if you have these percents out, you're going to end up, okay, which one do I have? Do I have benzene or do I have acetylene? That's the question. Does everybody see how this can be a problem?
Yeah.
Now let's turn in the book and read about this.
Formula. How is this possible?
3, 4, 6.
Remember that the subscripts in an empirical formula indicate the simplest whole number ratio of moles of the elements in the compound. However, the simplest ratio
Determine molar mass of acetylene. You're going to have to do an experiment other than just determining what elements are present in your unknown substance. You're going to have to determine an experiment that is going to either identify the acetylene, you could react it with something else, or you're going to have to do an experiment where you have separated from everything else and then either put it on a balance and do some other type of measurement there. I'm not sure. I'm not an expert in determining the molar mass of a unknown molecule, so I'd have to research that a little bit. I'm just be straight up with you. But you're going to have to do it somehow. There's an experiment that can be done or wouldn't be written there. The important thing to know here is that you're going to look for the empirical formula. So that's when we go back up here and we look at, who said the empirical formula earlier? Yeah, but what's the empirical formula here? of this, we've got, these are molecular formulas. What's the empirical? Yeah, CH. Now, does CH exist? No, CH does not exist. This is not a known compound, right? CH is not a known compound, but it's important for us because it's going to help us determine what the difference is between these two. So you have 12 plus 1, so the mass of that is 13. What did we get? 2. So then you're going to take 2 times CH, and you're going to get C2H2. So that's your formula. That's how we do this. That's why the empirical is important for us, because without it, we would not be able to identify these various substances that can be produced. Right. Yeah, this is 12 plus 1 is 13. Yeah.
You want to know what it is, you can take it to your lab, you can run it through a machine, and the machine will tell you that it's 48% carbon, 8% hydrogen, 43% oxygen. So what's the chemical? Well, we can get clues based on this percent composition. The empirical formula that we're at, and then adjust those so that they're a low whole number ratio. All right, step 1. Divide each percent by its atomic mass. Let's do this. Carbon, 48.38% divided by its atomic mass. There seems to be 1.5 to 3 to 1. There's always going to be little rounding things that you're going to have to watch out for. Be okay with rounding. Don't round too much, but if it's a 0.9, round it to the whole number.
Is that right?
Correct. I'll do the next one.
Oh, that's just 1 and 1, right? Is that 1?
Yep.
Oh, do you need me to add all these together now?
Now what you're going to do, you're going to divide by the smallest number. So if you divide by 3.39,
So-
by 3.39, that'll give you 1 there. And then you're going to divide the 5.08 by 3.39.
Since we're rounding this. Should I round?
Mm-hmm. 1.5.
Should I go to the second one?
No. And then 3.39 divided by 3.39 is 1, right? All right, so now you have 1, 1.5, and 0. So what you're going to do to get this a whole number? That is 1.5.
Add it together.
No, multiply times 2. So it's going to be 2 times 1.
So,
2 times 1 is 2. Okay, right, 2 equals 2. And then 2 times 1.5.
is 3. Yeah. Right?
And then 2 times 1 is 2. Yeah, so your formula is going to be C.
Oh, so it's 2
Nice job.
That the subscripts in an empirical formula indicate the simplest whole number ratio of moles of the elements in the compound. However, the simplest ratio does not always indicate the actual ratio of the compound. To identify
Experimentally determine the molar mass of acetylene. So one thing you could do, one lab that you could do, you could determine the molar mass of an unknown solid by freezing point depression. Well, we probably won't do it in the lab just because the temperature is required. We won't be able to provide that equipment. Changing its shape, going from a liquid to a solid. The solid always has what type of shape? Starts with a D. Solids always have definite shape. moles of solute per kilogram of solvent. Right, that's molality. So here they're showing you that the magnitude of the freezing point change is proportional to the molality of the dissolved solute. So this change in freezing point is proportional to the molality right there. So you can see how they are calculating the molar mass with a change in temperature. So the main point here is that most substances do not have the same freezing point and boiling point. So if one substance is going to freeze at a different temperature, then you can separate them that way, and you can then determine the mass of it. So that's a definite key to be aware of. Also, if you look at the melting points as well, you can separate substances by melting one off and the other one that didn't melt. You could then measure its mass. A lot of substances have water in them. Copper sulfate has 5 molecules of water. Now if you had water and you basically heated this to remove the water, would that be a physical change or a chemical change? Yeah, it's physical. Good job, Zane. Yeah, it's still copper sulfate, right? All you did was remove the water. Now, when you do that, you got to change its color. If you put the water in there, it's going to be blue, and if you take the water out, it's going to be white. So you got that color change. So that's just a physical change. But you might want to know how much percent water is in this substance. So we have the molar mass of the copper and the sulfate here. There's 4 of them, 159. Then we have our waters, 18, right? So we have 5 of them. That's going to be 90. So the total mass, you add them together, you get 249. So 159 from the copper sulfate, 90 from the water. So then over here you can determine just how much water is present compared to the copper sulfate. So if you put the 159 for the copper sulfate, it's around 63% copper sulfate. So it's going to be what, around 37% water. 36.1%. So that's a lot of water. And if you're buying copper sulfate, you would care about this. If they're selling you 36% water, a lot of people won't like that. They're like, just give me pure copper sulfate at the plant. Just get rid of the water. I can add water at my station, at my lab station. So when people start thinking economically, Trump's doing that right now with the tariffs. People start thinking, what can I do to, improve my profits? If you're selling me water, 36%, I can get water out of the sink, right? And now what you're going to do, you're going to divide by the smallest number. So 3.39 is the smallest number. Divide all of them by 3.39. Have the 1.5 here. It has to be a whole number. So what are you going to do to get this to be a whole number?
Add another one.
Multiply times 2. Because 1.5 times 2 is what?
2.
1.5 times 2 is 3. So you're going to put equals 3. Then you got to do the same thing to this though. So you did the same thing to 1, so it ends up being 2, 3, 2. So your formula is going to be C2 and that's correct. Peroxide, H2O2, that's a molecular formula. Now the empirical is the simplest whole number ratio, which would be HO. This is a 1-to-1. Does everybody say that's 1-to-1? Now water does not fit into this group. Water is what? It's 2-to-1, right? So if you had, let's say, a molecular formula that doesn't exist, let's just say we're going to hypothetically say that we had H8O4, right? So let's just say this was a molecular. Water would be the empirical because you can't simplify less than that. Does everybody understand that? So these two would be in different groups. This would be the empirical for a peroxide. This would be the empirical for this. Now in this situation, this does not exist. Does everybody see that? H8. Let me get some of that H8O4. No, doesn't happen. Now in this situation, HO does not exist. So sometimes the empirical formula exists and sometimes it doesn't. So in this situation, you're not going to go out and buy this. HO basically is OH and it's an ion. And that's different from a compound. So we're talking here about compounds. But we'll solve for the empirical because the empirical is going to help us determine what the unknown formula is. So we're going to show you that here in just a second. Benzene and acetylene. CH is the empirical here, another example of one that does not exist. Now when I was in college and they were telling me about things that do not exist and how they're important, it kind of like over my head a little bit. But once you start studying a little bit more, oh yeah, that makes sense. So you add the 12 plus the 1, you get the 13, right? So this is 13 grams. Now in the text they're telling you that the mass of the benzene we just calculated is 78. So they have to tell you the molecular. Now how do they calculate this? You might know how they calculate this? In the textbook there's telling you that they have to experimentally determine the molar mass of acetylene. How could they experimentally determine it? Anybody know? They can use freezing points. Not every substance has the same freezing point. So you can separate things by freezing them. You can use melting point. You could probably use density. So things can be separated based on their mass. Density is mass over volume, right? Make sense? Alright, so they're going to have to tell you what the mass is of the substance. They've got to be able to separate it and say, yes, the mass of the substance is separated. That's a good try. They've already given it to you there. That means they've experimentally determined it. The question is, how would you do that? How could you experimentally determine the molar mass of a substance? No, I'm talking about doing an actual experiment. What kind of experiment would you do? Okay, close. You could do a chemical reaction, right? And it could form a precipitate. And it falls out to the bottom of the solution and you pour off the water. Is everybody clear? Like we form precipitates in the lab. So you could find the mass that way. You could also do a freezing point change. Different substances have different freezing points, so you could separate it by freezing point. You could separate it by melting point. So there's some things that you could do to find the molar mass there. Now up here on the board, the empirical formula for acetylene and benzene is what? You might know what the empirical formula here is in this situation. What's the empirical formula here? Jaden, what's the empirical formula for these two substances? No, that's the molecular formula. These are both molecular formulas here. I want to know what the empirical formula is. No, in this situation, CH is the empirical. Why is this the empirical? It's the simplest whole number ratio. Does everybody see this is a 1-to-1? And this is a 1-to-1, right? So this is 1-to-1. Now, is CH a substance? Is it a compound? No, this does not exist. Does, I'm going to write this down, not exist. CH doesn't. We care about CH because it gives us a base point of reference of 13. So once we find out what these unknown masses are, we can figure out what it is. So in the text it tells us that we have a mass unknown of 26.04. So we take our 26.04 and we're going to divide by 13. And that's going to be around 2. So we take CH and we're going to multiply it times 2 and we get C2H2. Now let's take a look at one of the problems I gave you.
composition and the same. What is it? Biggest points.
Empirical. Empirical.
Empirical.